My name is Sebastian. My teammates Jorge Cisternas and Jackson Fatally. Our advisor is Dr. Indra Tamante, who will be presenting the solar-powered radio-controlled aircraft. Problem statement for our project is to optimize, manufacture, and build a solar-powered aircraft. A brief background on flight mechanics and on plane to fly. An aircraft has four main forces, which are weight, the drag, which is caused by the friction of the airflow against the skin of the aircraft, the lift, and the thrust. Here you can see the airfoil, which is the aerodynamic shape, in this case on the wings, which divides the airflow, which causes higher velocity on top and lower pressure in the top layer, and slower velocity at the bottom with higher pressure, which lifts the plane up. In conventional aircraft, the thrust is created by the combustion of jet fuel into the engines. In this case, we'll be using solar cells to create our power. They excite the electrons on the semiconductor material, which gives the electricity to our engines. The motivation for this project is to design an eco-friendly aircraft. We said before, we will manufacture a low-cost, continuously operated unmanned aerial vehicle. And to be all part of the Aerospace Engineering Club, motivation comes from doing so well in the SDO Aero Design Competition sponsored by Lockheed Martin. We want to keep doing research on all these aerostructures and keep competing and designing.
So for this project, we have three main objectives. We want to achieve a sustained solar-powered flight. We also want to reduce the cost of manufacturing such an aircraft with these characteristics, given the fact that the ones that are out there in the market are very expensive. We're going to provide a low-cost alternative to build one ourselves. We also want to determine the best configuration for our materials using carbon fiber, fiberglass, and chemical. So as Sebastian mentioned, our plane will be powered by solar cells. These solar cells will be released on the largest surface area of the airplane, which is the wing. And after doing some research, we found out that the best, most efficient, affordable solar cells out there in the market for us are monocrystalline cells, and they're high efficiency, low cost, and they're flexible. So it gives a lot of flexibility to put them on the wing. We have also done some initial design testing, on these cells, as you can see in the next one. So this is a table that we made. We have purchased three different cells, and we have measured the current, voltage, and power. It was done at 4:30 p.m., but what we plan on doing for further research, we plan on testing at different times during the day, all three cells at the same time to see which one gives us the greatest power. These are some of the design constraints that we have for this project. We have a limited budget, we have low rated power, we want to maintain low weight, and we have limited energy from the sun, given the fact that sometimes it's cloudy here in Miami, so that's another constraint we have.
So I'm going to talk about the design specifications. As George said, we're very limited on our power. In the current configuration that we're testing right now, we get around 220 watts from the sun, and continuous operation power requires around 180 watts. Obviously, as the plane banks and turns, you will reduce the efficiency of the solar cells because they won't be at a perfect angle with the sun, so you lose power. To combat this, we have to choose a very efficient design. We need to decrease the weight as much as possible and increase the lift-to-drag coefficient ratio in order to decrease the amount of power required to maintain level flight. For this reason, we've chosen a glider sailplane type plane design, which will use a folding propeller in the front of the aircraft and solar panels on the wings. We hope to target a 60 plus lift to drag ratio, and from our current simulations, we've exceeded that. Some of our design alternatives include configuration for the plane. We tested traditional tail, T-tail, and then we've run a plethora of optimization and analysis on many different airfoils and wing configurations. The first airfoil design alternatives include optimizing for max CLCD, which is the lift-to-drag coefficient ratio, which directly affects the efficiency of the aircraft, as well as the endurance of the airfoil. Endurance basically equates to how far you can go based on the efficiency of the aircraft. Shown here is some of our simulation and analysis done in XFLR5, which is a X-foil 2D and three-dimensional low-velocity Reynolds and laminar flow analysis program for airfoils. Shown here is just some of the highest performing airfoils that we tested. We ended up choosing the WE355 9.3 airfoil, which will be shown later. because it had the highest CLCD and endurance over our operating range of Reynolds and alpha values. Our traditional tail alternative was not ultimately chosen. We had to optimize for landing and takeoff conditions, level flight, in-flight maneuvers, and our ability to launch and land the airplane. Some of the reasons that affect this include the way we launch the aircraft. In traditional gliders, most of them are either self-powered, so they take off on a runway with some kind of power and then they glide after that, or they're towed or winch launched. For our specific aircraft, we are hoping to either tow or be able to hand launch our plane. For this reason, we didn't want to use a large horizontal stabilizer that was very close to the ground plane of the plane because it could have incidents with the ground or with launch rails when we're launching the aircraft. It also decreases the efficiency of the plane because in RC scale, the horizontal stabilizer is so close to the actual wing that the turbulence from the main wing affects the efficiency of the horizontal tail, which decreases the overall lift-to-drag ratio of our plane. A T-tail configuration, as shown here, was chosen because it presented the opposite of the traditional tail configuration. It removed the horizontal wing stabilizer from the ground plane of the plane, which makes it less likely to impact any objects and result in complications during takeoff and landing. And it also places it outside of the turbulent conditions produced by the main wing during flight. We've completed some basic wing loading analysis in order to help design the wings. Shown here is our estimated wing area, wing loading, and aerodynamic load for the half wing, which we are using to complete cantilever beam analysis. Shown here are some of our initial values using a stressed skin and a structural beam design. We're hoping to use a combination of both to reduce the cost and the weight of the total plane. This also helps with the manufacturability of the plane, as a fully stressed skin design is extremely difficult to manufacture.
You can see some of the standards we're going to be using for our plane. The American Society of Mechanical Engineers for the design and safety codes. The Federal Aviation Administration restricts us from flying the aircraft above 400 feet when there are planes in sight. We have the American Society for Testing of Materials for all the testing of all the material. The IABE, which for the correct use and vocabulary of our solar cells, and the Academy of Model Aeronautics required us to be members in order to fly our RC aircraft. Here are some of the global design components, which include the operability of the aircraft. Pretty much we can operate the aircraft anywhere in the world since it runs on solar power. We will include a multilingual user's manual with at least 3 languages, including English, French, and Spanish. Many of our components can be sourced globally, such as our solar cells we were purchased from China. And most of our materials will be recycling, including, for example, the batteries that we plan to add to the aircraft. Some of the contemporary issues we have the aircraft is the available technology. Solar cells do give us the amount of power we need to fly the aircraft, but if we had more advanced technology or we had a way to absorb more power from the sun, we could change the design and add more speed or maneuverability to the aircraft. We're also certainly the use of the aircraft versus airlines or autonomous drone use. And here are the lifelong learning experiences we've had. We've learned to collaborate with our engineering disciplines, which I believe are beneficial to all engineers. We collaborated with electrical engineers for the use of our solar cells. We learned a lot about the design of aerospace structures, which are now a main theme in the mechanical. For example, we learned about the sizing of the tail depending on the size of the wings of the aircraft. We've learned a lot about modeling and simulations in SolidWorks, for example, or ANSYS. We had to do a lot of testing on this aircraft. And most importantly, the teamwork, which also believe will be very important collaborating with engineers and for our future careers.
So here's our projected cost. As you can see here, we have divided it into different components. As you can see from the total price, it's a little bit high, but we have already applied to some grants and we plan on developing a sponsorship package, just as we did for the Aerospace Engineering Club to get funding for this project. Here's the division of responsibilities between the 3 of us. It's important to note that whether someone's doing research and another one's doing conceptual design, we will all collaborate between one another to make sure that we're doing this the correct way. Here's our timeline. As you can see, most of our work this semester has been in the conceptual design, finalizing the different design alternatives, developing a budget, And we will, in the summer, we will concentrate fully on fundraising and optimizing our final design. And in the fall, we actually manufacture and build the aircraft. In conclusion, our final design was chosen, an initial budget was developed, and we were able to choose the best, most efficient solar cells, which are monocrystalline. And for future work, we will do some computation fluid dynamics on ANSYS. We will develop a linkage structure between the wing and the fuselage. We will also secure the funding for this project, and we will heavily focus on manufacturing and assembling this aircraft. We'll open the floor for questions.
So what are you controlling with the radio control?
The entire aircraft.
So walk me through what.
Okay, so in conventional remote control aircraft, you have some kind of wireless transmitter, right? You have a radio, and you have a receiver that's on the aircraft. So the receiver controls all of your control surfaces and your thrust. And through that, you can then fly your aircraft, right? So, whatever control inputs you have. For our case, because we're looking at a high endurance aircraft, we're going to have some kind of electronic control and stability system, including a gyroscope and accelerometer. And we hope to implement eventually a GPS guidance system so that we can remotely map our aircraft without having to constantly control it. As this is a long endurance, high endurance aircraft, our expected flight times are around 5 to 6 hours, which is extremely fatiguing for any pilot. So we hope to assist this control with electronic assistance.
And what kind of range are you going to get out of a radio control system?
So modern radio control systems are actually pretty efficient. Very small, low power setups can easily attain a range of 2 kilometers, which in retrospect for a project like this is not actually all that much, but there are very long range systems that have been developed which can reflect over the horizon and achieve ranges of 25 to 50 kilometers.
But what are you planning to do here?
With this aircraft, we hope to apply it to wildfire monitoring in California, to use it as an autonomous platform, fly it basically all day in the summer, and have a thermal imaging camera that can send back GPS coordinates to then monitor where wildfires are beginning or where they're sparking. And then once those coordinates have been sent down, using some kind of positioning or telecommunication system from the aircraft, you can send in firefighters to stop the fire before it becomes a humongous blaze.
This has got flaps, I assume?
Yes.
So you have the ability to land it?
Yes. Well, right now we're actually working on optimization for the wing. Right as of now, the current configuration, our takeoff velocity is only 15 miles an hour at an 8-degree angle of attack, so hand launching is not out of the question. That was one of the things we wanted to make sure we could complete with the aircraft. Current cruise velocity is estimated around 23 to 25 miles per hour, which is extremely slow, but because it's going to be a long endurance aircraft, that doesn't really matter all that much. We could optimize for higher speed and higher maneuverability, but then we have to change the wing plan, you lose efficiency, and you get less solar power.
So you can shut off the prop?
Yes,
with remote?
so the optimal flight plan for a plane of this design is you use your power, just like the solar power plane that just landed in San Francisco. I'm forgetting the name of it at the moment.
Solar impulse.
The solar impulse. So during the day when you have the highest power, or in our case, when you're flying at a direct angle to the sun so that you have the highest incidence of solar radiation, you power up your propeller and you climb to a higher altitude, and then at a higher altitude you can turn off the propeller and use the high efficiency to then glide down while recharging a small battery. So the battery kind of acts as like a capacitor between the solar output and your motor draw. So while our plane is designed to run continuously, you can shut off the prop if you need more power and you can just glide.
I have a question. When you're flying the plane, do you plan to use thermal updrafts to heat in the sky?
Yes, so that's one of the big things about gliders is that most of them stay airborne for so long because of thermals. Our specific plane is designed to be able to fly without thermals as long as we, aren't going under clouds and things like that. As long as there's enough solar energy, we should be able to maintain a zero sink rate with minimal power. If required, we could use thermals. Thermals for solar craft are not optimal though because you have to go in and out between edges of clouds, which then reduces the solar power.
For testing, you guys only, scheduled 1 month. Do you guys think that'll be enough for you guys to complete the project? Or do you get enough data for testing?
I mean,
during the timeline?
for testing as far as the final design? Or,
In your timeline, you
Yes.
have only 1 month restored for
Yes,
testing?
but it's gonna be we have already started testing the solar cells and the different components we plan. This is just for final testing, as far as when the whole every component is assembled.
So each individual subassembly has already gone through some amount of simulation and analysis. Obviously, we have to test each system as it's completed, but the entire plane altogether will have to be tested once it's completed, which is why that's listed there in November.
Now, you talk about having a low-cost, continuous operating unmanned aerial vehicle.
Yes.
Low cost compared to what? I mean, I suspect
So that's a valid point. $4,000 is not a trivial amount, but compared to our current competition, which is far bulkier, far more expensive, and far more technical, this plane really fills a niche that isn't offered by anything else at the moment. Current competitors range in the 20 to 25 foot wingspan area, are available only through military contracting or through people working on the projects themselves, and it costs anywhere from $20,000 to $50,000.
okay, make sure that you emphasize that point in your report, in your senior report. Right?
Yeah.
So, now, also you talk about in your proposed design about having high efficiency.
Yes.
What is that level of efficiency that you're looking at?
So we're measuring efficiency through our lift to drag ratio. Basically, for the airfoil analysis done on the main wing, how much lift do you get for a certain amount of drag? The other optimization parameter for efficiency is the endurance, which is how far you can fly with a certain amount of thrust. So for our specific aircraft, we only have a limited amount of power, right? So we want to increase the distance we can fly on that limited amount of power. Ideally to the point where we have so much efficiency that even with our tiny amount of power we can fly indefinitely as long as there's sunlight. Other aerodynamic efficiency includes turbulent transitions and laminar flow bubbles. At our extremely low velocities, we might actually have to add turbulators to the top surface of the wing to induce a laminar separation into turbulence, because otherwise you get laminar separation bubbles.
But numerically, what
Oh,
value?
okay.
What value?
Yeah, so theoretically, the airfoil that we are currently using is 100% efficient in fully laminar conditions because the transition on the top and bottom surface of the airfoil is theoretically at the very end of the airfoil. What this means is that you have a maximum gradient between the velocities and the pressure differentials on the top and bottom surface of the airfoil. In practice, that's obviously not going to be correct. There's always impurities on the surface of the airfoil, and any maneuvers that change the Reynolds value where it's optimal will decrease the efficiency. We're hoping to get a power density efficiency of around 85%.
Also, our solar cells that we have purchased range between 20 to 25% of solar efficiency.
Thank you very much.